A 400-ton piece of steel traveling at 200 miles per hour generates a staggering amount of kinetic energy. To bring that mass to a halt, traditional systems rely on a brute force method. They press two physical surfaces together using aggressive mechanical friction to convert all that forward motion into heat. Grinding metal against metal at those speeds is highly destructive. It creates intense thermal spikes that warp components, shreds the physical brake pads, and scatters toxic chemical dust into the environment. For transit networks, this requires pulling trains off the tracks for constant, rigorous inspections. Continually replacing worn-out brake pads adds massive operational downtime and financial costs over the lifespan of a single vehicle. As engineers push for heavier train cars and faster routes, relying on physical contact to stop them reaches a breaking point. It rapidly becomes an entirely unsustainable bottleneck. This creates an engineering paradox. How do you apply immense stopping power to a wheel without actually touching it? The solution is the eddy current brake. Instead of mechanical pads, it harnesses the invisible resistance of electromagnetism. By completely removing the physical connection between the brake and the track, engineers eliminate the physical wear and tear that has historically limited the speed and safety of heavy machinery. We can see the mechanics of this with a simple lab experiment, dropping a permanent magnet down a hollow copper pipe. As the magnet falls, its moving magnetic field passes through the conductive copper. This motion induces small circular electric currents, known as eddy currents, inside the walls of the tube. This is governed by Lenz's law, which states that an induced electric current creates a magnetic field that opposes the change that produced it. Because of this, the swirling currents in the copper generate an upward magnetic force that actively pushes back against the falling magnet, slowing its descent. This microphenomenon creates proportional magnetic drag entirely out of motion, and it is exactly the mechanism engineers needed to catch heavy vehicles. To apply this to a roller coaster, you take that copper tube and unroll it into a flat, linear track. Instead of a falling magnet, highly conductive metal fins are bolted to the sides of the passenger cars. These fins rush past a series of stationary magnets mounted near the end of the ride. As the heavy metal fins slice through the magnetic fields at high speed, they induce massive eddy currents. The car's kinetic energy is instantly converted into powerful magnetic drag, safely and smoothly slowing the train. Roller coasters use permanent magnets for this, magnets that generate their own constant field without an external power source. This means the braking system requires zero electricity to function. If the power goes out, the magnets still work. It is a completely fail-safe way to decelerate human-rated transit. When you scale up to a high-speed commuter train, the brakes can't be permanently fixed to the end of a track. A driver needs to actively toggle them on and off during the journey. Trains like the German ICE-3 use a linear approach. They mount electromagnets on the wheel bogies, the structural chassis that holds the train's axles. These magnets hover just 7 millimeters above the steel rails, inducing electromagnetic drag directly into the track below. Older Japanese Shinkansen trains use an alternative circular eddy current brake, where the entire system is contained within the wheel assembly itself. By increasing or decreasing the electrical current sent to the coils, engineers can apply precise, variable braking force to a spinning metal disc without ever making physical contact. Whether the drag is induced into the rail or an onboard disc, these electromagnetic systems solve the problem of physical degradation during high-speed deceleration. But there is a catch to frictionless braking. The strength of the magnetic drag is entirely dependent on the speed of the moving conductor. This chart shows vehicle speed on the x-axis and braking force on the y-axis. As the vehicle slows down, the induced eddy currents weaken. When the speed reaches exactly 0 miles per hour, the braking force drops to absolute zero. Because there is no holding force at a standstill, a train cannot use magnets to keep itself parked at a platform or stopped on an incline. Traditional friction brakes are still required to secure the vehicle. The eddy current brake operates as an assistive technology. It handles extreme energy management at high speeds, while mechanical systems handle the final stop. There is also a thermodynamic reality to consider. The massive kinetic energy of a 200-mile-per-hour train doesn't simply disappear. The swirling eddy currents convert all of it into heat. With linear brakes, that heat is dumped directly into the steel rails. In busy approaches to a station where multiple trains brake in quick succession, This localized thermal load can cause the tracks to expand, warp, or structurally fail. To address this, modern engineering is shifting toward regenerative braking. Instead of turning kinetic energy into useless heat, regenerative systems use similar magnetic principles to run the electric motors in reverse, capturing that momentum as reusable electricity. Eliminating the brake pads solved the problem of mechanical wear. Now the goal is capturing that energy and putting it back to work.